Right. Uh, Guys, good evening. So we are starting to discuss fluid mechanics, past paper question discussion. Because you asked to discuss the questions of from electricity and fluids, right? So let's start from the hydrostatics. We'll continue to discuss the rest of the questions, right? So hope you're studying really well, and as the as the exam not gonna postpone, right? So you'll have to face the exams by the exact day. So hopefully, so for the students who came to my class, have nothing to worry about. We have finished the syllabus 3 months before the August, and we started doing the full papers and fast revisions and the question banks and everything. So so far we have done a lot, and we'll be continuing to do more, and there'll be a full night on practicals in the structured essays soon. I will tell you, right? Join to the practicals night as well, so you can cover many of the structured essays. That's basically for the structured essays, right? That's basically for the covering structured essays. So join the full night as well. So let's see. Right, come to this one, hydrostatics. The weight of a glass stopper when measured using a spring balance in the air is 2.4 newtons. When it is fully immersed in water, the weight is 2 newtons. So 0.4 newtons of upthrust is there. The density of the water is 1000 kilograms, and the acceleration of gravity is 10. The density of the glass stopper material, in kilogram per cubic meter is. So now this is sort of a relative density question. If you remember, there's this equation, density of the, is the whiteboard now? Whiteboard, this one I hope. So there's this relative density equation, relative density equal weight of the object divided by the upthrust, right? So here the weight of the object is given as 2.4 newtons and the upthrust is 0.4, because when you put the glass object, like when you immerse the glass object in the water, the weight is reduced to 2 newtons, which means 0.4 newtons of a upthrust is there. So the relative density of this then should be, now 2.4 divided by 0.4 means 24 divided by 4, right? So 4 times 1, 4 times 6, right? 6. 4 times 6. So the relative density is 6, which means the density of the object should be relative density multiplied by 1000, because relative density is density of the substance, right? Relative density is again density of the substance, or let's say the object, divided by density of water, right? So if you cross multiply the relative density of any substance by the density of water, you'll get the density of the object over or the substance, right? So dO should equal to RD into dW, or the density of water, which is 1000. So RD is 6, density of water is 1000. So 6 into 1000 is 6000 kilogram per cubic meter, right? So this is the density of the glass, what was that, glass stopper, right? The answer is 6000, right? Answer is 6000, right? Second one, consider the following statements on the mechanism of hydraulic brake system of a motor vehicle. The brake activates due to the transmitted additional pressure by the force applied on the brake pedal exerted on the liquid in the main cylinder to the piston in the brake cylinder. Right? They're asking true statements. Okay. Now the brake activates due to the transmitted additional pressure by the force applied on the brake pedal exerted on the fluid in the main cylinder to the pistons in the brake cylinders. That's so far okay. B. An increased pressure created due to the additional pressure applied on the fluid by the pedal is exerted on the pistons in the brake cylinder. Okay. C. A frictional torque exerted on the brake disc due to the additional pressure on the piston in the brake cylinder. So they seems to be all correct, right? So in a brake system, what actually happens is the Pascal's law. When you apply a small force, it continues to be same through the incompressible liquid. So if the liquid is incompressible, uh, the applied pressure continues to be same through the liquid, right? And since when you change the area, the forces supposed to be changed, therefore you be applying maybe a small area of a force on the brakes, and this pressure that occurs on the brake is transmitted to the brake pedals, and in the brake pedals the surface area is really high, right? The surface area is really high, so the force will be increased. So the actual formula is F1 over A1 equals F2 over A2, which means like something like this, right? Something like this. So here the area is low, right? And let's say F1 of a force is applied. Here the area is large. Therefore, when you apply F1 of a force in A1 of a small area, and when you increase the area, the force will be increasing in the times, how many times the area has increased. Let's say the area is increased twice, so the force will be increased twice as well, right? The brake activates due to the transmitted additional pressure by the force applied on the brake pedal exerted on the fluid in the main cylinder to the piston in the brake cylinder. That is okay, that is okay, that is correct. An increased pressure created due to the additional pressure applied on the fluid by the pedal is exerted on the piston in the brake cylinder. Even that is true. C. A frictional torque exerted on the brake disc due to the additional pressure on the piston in the brake cylinder. A frictional torque exerted on the brake disc. එතන මේ තින්නේ ටයර් එක නම් මේකේ brake disc එකක් තියෙනවා නේ මෙහෙම. brake disc එක මෙහෙම අල්ලනවා ටයර් එක. So a frictional torque exerted. එතකොට මේකේ frictional torque එකක් එනවා. මෙහෙම ඇල්ලුවාන් පස්සේ මෙයා මෙහෙට කැරකෙන්නේ. Tries to rotate this way. So there's a frictional force against it. So due to the frictional force and the rotation, there's a torque, right? There's a torque. A frictional torque exerted on the brake disc due to the additional pressure on the piston in the brake cylinder. And that is also correct. So far, all the three answers are true. Only A and B are true, only A and C are true. There's only two answers correct given. You have to check on that. The frictional torque exerted on the brake disc due to the additional pressure on the piston in the brake cylinder. On the piston. Okay. Now let's read from the first one again. The brake activates due to the transmitted additional pressure by the force. Brake activates due to the transmitted additional pressure by the force applied on the brake pedal exerted on the fluid in the main cylinder due to the cylinder to the piston in the brake cylinder. That is all good. An increased pressure created due to the additional pressure applied on the fluid by the pedal is exerted on the piston in the brake cylinder. That is also good. A frictional torque exerted on the brake disc. On the brake disc. Okay. Due to the additional pressure on the piston. Due to the additional pressure. Due to the additional pressure on the piston. The brake cylinder. So like there's no additional pressure because it's an additional force or an increased force applying on the disc, because now if you think about this pressure is so far the same, right? Pressure is so far the same, but the friction, like the force is increasing, right? Just hold on for a second, we'll check that answer. The answer to check. This is right. So in the statement B, an increased pressure created due to the additional pressure applied on the fluid by the pedal is exerted on the piston in the brake cylinder. So the question says an increased pressure created due to the additional pressure. So this pressure created due to the additional pressure applied on the fluid by the pedal is exerted on the piston in the brake cylinder. As per the question, it says this is what it explains, right? I'm going to say what it explains. Like it seems to be true, like true to me, but this statement is false, right? So it seems to be true to me. An increased pressure created due to the additional pressure applied on the fluid by the pedal. So you're pressing the pedal. Because you're pressing the pedal, you apply a increased pressure on the pedal. So the pressure inside the liquid also getting increased, and it is exerted to the pistons in the brake cylinder. So the brakes are working, right? So as per the question, it like the answer, it says B is false. Pressure is not increased or multiplied during the transmission. That is true. Pressure is not increased in the transmission does it say anything about the pressure is increased in the transmission? An increased pressure created due to the additional pressure applied. So yeah, so when you apply the force on the pedal, the pressure supposed to be increased. An increased pressure created due to the additional pressure applied on the fluid by the pedal is exerted on the piston in the brake cylinder. So anyways, the answer says the pressure does not increase in the liquid. True, if when you apply a force, the pressure that occurs inside the liquid will continue the same way to the other side. That is the Pascal's law, because the fluids does not compress. The fluid does not compress. The pressure continues to be same throughout the liquid. So as per the scheme, the answer is actually A and C, right? Only A and C are true because it says the pressure is increasing. So of course the pressure should increase when you apply a force, right? Because the pressure there was, and the new pressure should be increased. So like anyways, as per the Pascal's law, the pressure can't increase in a liquid, and by that term they have taken the B as a wrong answer, right? Come to the third one. The speed at which water flows through a uniform rubber tube with 1 square centimeter internal diameter is 2 meters per second. If a nozzle with 0.2 square centimeter internal diameter is fixed at the end of the, I'm sorry, this is centimeters, of course, diameters, right? Not the area. Internal diameter is fixed at the end of the tube. The speed at which water is emitted from the nozzle is. So now there's velocity, there's the diameter, right? So you just have to take continuity equation, which is A1 V1 equals A2 V2, right? A1 V1 equals A2 V2. That is the equation, right? The equation you're supposed to use is A1 V1 equals A2 V2, right? A1 V1 equals A2 V2 is the equation. So in the first one, it doesn't say about anything. It doesn't say anything about the cross-sectional area, but it says about the diameter, right? So the diameter is 1 centimeter in the first one, and the diameter is 0.2 centimeters in the end, right? So I'll draw it. So it's something like this. It's something like this. Right? Something like this. So it's 1 centimeter of a diameter at the beginning and 0.2 centimeter of a diameter at the end. The water flows through this, right? The water flows through this, right? And the velocity at the beginning is 2 meters per second is given. They're asking for the final velocity, right? They're asking for the final velocity, right? Right. So that should be A1 V1 equals A2 V2. So you have to apply it. So now cross-sectional area is 5r square. So the radius of this should be half of the diameter, which is 1/2. So I'm going to put 5. R is now 1 divided by 2. So 5r square. This is the cross-sectional area of this one. Into velocity is 2 ms minus 1 equals cross-sectional area of this one is 5. The radius is 0.1. 0.2 divided by 2 is 0.1. We'll take it as 1/10 because 1/10 is 0.1 and it's square into V2 is the equation, right? So now 5 to 5 cancels out. 1/2 square will be 1/4 into 2 equals 1/10 square is 1/100 into V2. If I cross multiply this, that will be 100 divided by 4. That is 25. 25 into 2 is 50. So 50 meters per second of velocity should be there in the edge of it, right? Yeah, so it's 50 meters per second, right? Take a note quickly, right? Take a note quickly if you want. Right, so come to the fifth question. A fan with effective area of A moves air of density rho, this is rho, density rho, at a speed of V. The required power for this movement is, right? They're asking for the required power for this movement, right? You are given the effective area is A, density of the air is V, sorry, rho, and the speed is V, right? So now, so these are the things, right? So I'm doing all these as I'm doing it for the first time, right? So the things like the flows and the things that I do the same way you should be or you would be doing in the exam, because people don't do things just by looking at it. You just have to think it differently. So I'm like letting you understand how you get into the struggle when it comes to the questions, how you get through it, right? So this is what I'm going to think, right? So this is the first time I'm doing it. Like, this is how I'm thinking about it, and there will be a struggle, bit of a struggle will be there, and that's okay. So air is flowing through it, as it says, as a cross-sectional area of A, right? And the velocity is V, and the density of it is rho, right? So now do we see that inside the rho, we will have to break these things down, right? So inside the rho, there's mass over volume, right? Inside the rho, there's mass over volume, and volume is anyways cross-sectional area into the length or the height, right? If it is a uniform thing, cross-sectional area into length will be the volume, of course. So if I take a volume of wind, that will be A into L. So I'm thinking in that way. Now this is the density of it. So if now this is rho, right? This is rho. So if I multiply this by A, that will be M over L for now. We'll keep it that way, right? And we have velocity, which is L divided by T, right? L divided by T. So now, if you multiply all this, all the L to L cancel out, A to A cancel out, mass over time, mass over time will be left. So that's not going to work. right? That's not going to work. We have to think in a different way. A fan with effective area of A moves with air density rho at the speed of v. The required power for this movement is. So this is half rho AV. Rho AV didn't work anyways. Rho AV square we can try, or rho AV cube, or there's rho half rho AV cube, right? If I try this one, rho AV square, right? If I try rho AV square, it will be something like this. If I tried rho AV square, right? So V will be squared, rho AV squared. This is velocity, right? So that will be m over, so A to A cancels out. Now there's L into L square over T square, right? And now 1 of L to 1 of L will cancel out. That will be ml, right? ml over T square. If I take it, take this in units, m is mass, kilogram per second, right? Kilogram meter per square second. This is basically force, right? This is basically force. So even force not gonna work, right? Force not gonna work. So we will try one of a cube here, right? A cube value is also there. We'll try the cube one, right? So did you understand that was force? And there's a cube as well, rho AB cube, right? So I'm gonna check rho AB cube. So did you understand that if we put rho AV square, the units will be kgms minus 2, and that didn't work. So I'm gonna put rho AV cube, right? Rho AV cube. That will be again the same. Mass over area into length into area into length over time cube of it, and that will be area to area cancels out, meter over L into L cube divided by T cube, that is m L square divided by T cube, right? If I take this, that will be to the units, m is mass, kilogram, length is meter, meter square, T is time, second, this, right? So now, if I derive something out of it, kg ms minus 1 can be derived out of it. Kg ms minus 2 can be derived out of it. 1 meter. Then another meter is left here. Right? Kg 1 m we took it out, but s minus 2 we took it out. So this is force. This is meter, the length, divided by 1 of a second is in the bottom. S minus 1 I took it to the bottom. Now this is force, right? This is force. This is displacement, that is in meters, and this is time. So force into displacement is work done. Work done divided by time is of course the power, right? That is power. So answer should be rho AV cube, right? In the units way, right? So the answer should be rho AV cube. We don't have to take the half because this itself gives you the answer, right? So this is how I took it, right? This is how I took it. This is how I derived it. Think in the terms of basic units. I derived it, right? I derived it up to this, and then I created the formula I want because it should be power, that is somewhat work divided by time, and work is force into displacement. So I extracted, or I derived force out of this, that is kgms minus 2. I took it out of it, and meter divided by time was left. So this is force. The meter is of course displacement. So force into displacement is work. Divided by time should be power. So that's how I took it, right? Think about it. Take a note. So it was taken in another, can be taken in another way as this. How? So now rho AB cube, if we took it that way again, now the A into V, right? A into V sort of gives you the volume per time, right? A into V gives you sort of volume per time, as we discussed in the continuity equation. So take a cross-sectional area like this. Area is this. This is the length. Area into length is volume, right? So length divided by time. Length divided by time is velocity. So this, if we took as V, A into V is, right? A into V is A into L over T, right? So A into L, cross-sectional area into length, is volume. So AV is anyways volume per time, right? Volume divided by time. So if AV is volume divided by time and rho is mass over area, right? Rho is mass over area. So rho equals mass over area, right? And if you multiplied rho with AV, right? Rho with AV, which means like rho AV is actually M over A multiplied by volume over, this is, sorry, mass over volume, right? This is mass over volume. Density is mass over volume. Mass over volume into volume over T, right? This is rho AV basically. So V2V cancels out. Rho AV is basically mass over time as we took it before, right? So if you put the half mv square to it, right? If you put the half mv square to it, like if you take the mv square of it, or mv square, now this is m over t, no? So if you put mv square over t, like half mv square over t, so half mv square over t, half mv square over t is again power, right? Half mv square over t is also again power. So if we convert this into half mv square, what are we supposed to do? So to convert this into half mv square, what we supposed to do actually is we have to take v square, right? We have to take v square, and this is mass, right? This is mass over time. So half, if we take the kinetic energy, that will be half. Instead of m, now we can take rho av, right? Because rho av is m over t, right? I'm going to take half mv square, right? So I'm going to put half mv square. So instead of m, we can take rho a v, right? Instead of m, we can take rho a v. Hope you understand that. Because rho a v is m over t. So forget about t. We need m for the half mv square. Now m, I will take it as rho a v, right? I'm taking it as rho a v. Now there's t as well. Let's forget about the t, right? So this is mass. Half m. This is mass, half m. V square is anyways the velocity square, right? So inside this, half m v, like half m over t, v square is there. Now if I take it rho a v as m over t, now half into m over t, v square is there now. You understand that? Half rho a v is m over t and v square, right? So now this part is what? Half mv square is kinetic energy, right? Half mv square is kinetic energy, and that divided by t is, of course, power, right? Is power. So inside of it, these three parts are there. What are the three parts? Half rho a v into v square will become v cube. So the answer given is this: half rho a v cube. So unit wise or fundamentally, without half, I took rho a v cube, right? But that I took as FD over T, work over time definition. But the answer is given in the kinetic energy over time definition way. So the correct answer is half rho AV cube, right? Half rho AV cube. So questions are a bit tough and it's really good, right? Fluid mechanics questions are a bit tough and it's really good. Right? I hope you understood it, right? Hope you understood it. If you didn't understand, you can ask me again. I'll explain it back again. So we went through fundamental unit stuff first. FD over S, work over time, that is power. Didn't work it that way. So we had to try something else. So we had m over t first. Then we put half m square. So instead of m, we took m over t. And the equation half m square over t gave us the power, right? Half m square gave the power. So go through it again, you will understand. Shall we go to the next question? I think these fluid questions are a bit difficult and the electricity questions are also difficult, but let's anyways go through it the same way how you're going through it, right? You're going through it the same way you're going through it. It's a bit of a struggle and it's okay, right? It's okay, right? Okay, so let's come to the next question. What is the next question again? This one, right? Fifth question, right? So the fifth question, I mean, I just liked it. Bro, come and watch the video now. Just I done today paper. Nice. Yeah, people are reacting, but I didn't check if they have joined the class. Please join the class and do the calculations with me. So yeah. So let's do this. Fifth one. The human heart discharge 74 milliliter of blood at a beat against pressure of 0.1 meter Hg. That's meter Hg that is given. If the pulse frequency is 72 beats per minute, the density of mercury is 13,600 kilogram per cubic meter, and the acceleration of the gravity is 10 Newton per kilogram. That's m is minus 1 anyways. The power of the heart is, they're asking the power of the heart. So how many beats? Let's do this. Human heart discharges 74 milliliters of blood at a beat against the pressure of 0.1 meter Hg. Come to the question back again. So this is your heart, and it's pumping the blood through the, say, aorta or something, through the aorta, and per beat it is pumping. Per beat means like per a compression it is pumping how many milliliters? As it says, it's pumping 74 milliliters of blood, and the pressure is 0.1 meter Hg. So this 74 milliliter is pumped against this much of a pressure, right? This much of a pressure is there. Okay. What does the question say? The density of the mercury. Yeah, because the pressure is measured in mercury, so we can calculate the pressure in pascals, right? Because 0.0 mHg is not actual pressure; it's a way of expressing the pressure. So if we have the density of the mercury, we can convert it into pascals. So it's good. Okay. And frequency is 32 beats per minute, right? So 32 beats or 32 press ups will happen per minute. The density of the mercury is given, and the acceleration gravity is 10 anyways. They're asking the power of the heart. Okay. So per minute, 72 of that will happen, right? Per minute, right? Per minute, or per 60 seconds, 72 of this, right? 72 of this will happen. And they are asking for the power of the heart, right? Let's do. Right, the volume is there, the pressure against is there, right? And let's convert this pressure first into Pascal. How do we do that? Because pressure is H rho G, right? Liquid pressure is H rho G. Now H is 0.1 meter, rho is 13,600, gravitational acceleration is 10. It's basically 13,600 pascals of a pressure, right? So this much of a pressure is there. So, right. So they are pumping, the heart is actually pumping 74 millimeters per time, which means per minute 74 into 74 milliliters into 72, the total volume, right? Total volume transmitted, let's say, transferred is this much, 74 into 72, and I need a calculator as well. 72 into 74. Right, 74 into 72 is 500, this much milliliters, right? Or you can take it as cubic centimeters. That is cubic centimeters. Milliliter is cubic centimeters basically. This much of a volume is there. So now pressure and volume are there. So pressure into volume basically is work done, isn't it? Pressure into volume, if you take it this way, PV is actually the work done. How? Because if you derive this, pressure is force over area, volume is area into height, or area into length or distance, anything. Let's take distance, area into distance, right? If it is a tube like this, if it is going to a tube like this is the cross sectional area, this is the distance. So the pressure is F over A, force over area. Now this is the area, and volume is cross sectional area into the displacement. Now PV, pressure into volume, A to A cancels out. There is force into displacement. That is basically the work, isn't it? So if you take PV, right? If you take PV, that is basically the work done. I gave this under the chemistry part. Which part? Standard heat of reaction. How to measure the work done. One of a way is FD, the other one is PV. I gave it in the tube. It's there. So W equals PV. The work done is PV. So they're asking for what? They're asking for the power of the heart. So this is the work done in a minute, and if you divide this by time, it will be the power, right? So if you divide this by 60, that is the power, right? So the power will be, right? Power will be PV, the work done, divided by time, which is 60 seconds, right? Because PV, basically the power is, I'll write it here, power is work over time, right? And the PV is work, and the time is 60 seconds or 1 minute. So how much is pressure now? 13,600 of a Pascal pressure, right? This should be divided, multiplied by the volume. How much is that? 5,328 cubic centimeters. You have to convert this into cubic meters. For that, you have to multiply this by 10 to the power minus 6. 5,328 10 to the power minus 6. And you have to divide it by 60 seconds. So this is P, this is V, that is work, this is T. This should give you the answer. So let's do. Hope you understood it. 13,600 into 5,328 divide by 60. That is this much. 1,207,680 into 10 to the power minus 6 is 1, 2, 3, 4, 5, 6. So it's basically 1.2 watts sort of a power. Is there any answer like that? Luckily, yes. Oh, yes. Can you check on that? Yeah. Did you understand that? So this is basically the heart. This is the aorta or any sort of a vessel. So the blood is pumped through this 74 millimeters per time. Again 0.1 meter per hg, 0.1 meter hg pressure, and per minute this happens 72 times, right? So first we converted the pressure into Pascal, 13,600, and we took the total volume per minute and we multiplied the pressure with the volume. That gave us the work, and we divided the work by the time spent. That gave us the power, right? That's how you go into the answer. Okay. Right, shall we do the next one? 6. A non-viscous fluid with density D has a streamlined flow in a tube with a variable cross section as shown in the diagram. So cross section area is varying. The axis of the tube is aligned horizontally if the fluid pressure is P at the point where the flow velocity is V. Okay. What would be the pressure at the point where the flow velocity is 5V? So anyways, flow velocity 5V should be here because this is narrow. So V should be here, right? And they're asking for the pressure. Okay. Now what else are given? The axis of the tube is aligned horizontally if the fluid pressure is P. The fluid pressure here is P at the point where the flow velocity is V. Okay. V is P. Like with the velocity V, the pressure is P. What would be the pressure at the point where the flow velocity is 5V and the density is D, right? Non-viscous fluid, so it's basically the Bernoullis you will have to put, as it seems like Bernoullis there. Okay, so if you put Bernoullis here, they're asking the what would be the pressure at the point where the flow velocity is 5, no? So it's basically Bernoullis you will have to put. So the pressure, if I take the two of the points here as x and y, let's say, so we have to equal the Bernoullis in the x and y points. What are the things we have to equal? Pressure at this point plus the half rho v square, or the kinetic energy in a unit volume, half. So the rho is actually d, density, v is v, so half dv square is the kinetic energy in a unit volume. We don't have to take the h rho g because if we compare two of the points, there's no any height difference. So if you put h rho g in the both the sides, they will cancel out. So you don't have to put it. Now this should equal to the pressure here at this point. I'll take it as Py plus half rho v square. Now in this case, the density is d, dv square. So the v square is 5v and it's square, right? Now these two should be equal as per the Bernoullis, right? And they're asking for the pressure, right? Pressure at 5V. So we have, that is Py. We have to isolate it. So if I isolate this, that will be P plus half dV square minus this one. You have to take this one to this side. So that will be half d 5V square is 25V square. It's basically 25 dV square, right? 25 dV square divided by 2. So if I deduct, like they have the common denominator, so the final answer should be P plus 25 dV square minus 25 dV square plus dV square will become minus 24 dV square divided by 2. So this is P minus, then it's P minus 24 dV square over 2, right? So the 2 to 24 cancels out, that will be 12. The final answer should be P minus 12 dV square divided by, there's nothing to divide. That's it. P minus 12 dV square should be the answer. The answer there? Yeah. Yes, is there. P minus 12 dV square. A bit of a fun questions, and we are already here. So P minus 12 dV square is there. So we actually, what we actually did was like we put Bernoulli's and got the answer on the way. So this is how you actually face the questions, just try with something, right? Just try with something. And if you know how to do the real application, how it actually works, you already know how the Bernoulli's work, right? And we have applied the Bernoulli's to sort of things like this, right? And it's the same thing, but maybe the values are different, and maybe a bit of algebraic formats are there. Still, it's the same thing. So if you try doing it that way and you keep simplifying it, you'll get the answer at the end, right? So that's how it happens. So take a note quickly. Right. So come to the next question, 7th question. The blood flowing rate from the heart of a person at rest is 6 liters per minute, and his volume passes through the capillaries at an average speed of 1 millimeter per second. A schematic of one capillary is given below. Assume that blood is an incompressible fluid having laminar flow. Okay. Pi equals 3, the number of capillaries in the body. Asking for the number of capillaries in the body. It's a good question as well, right? The blood flowing rate from heart of a person at rest is 6 liters per minute. So by heart, 6 liters per minute is released, right? So, and this volume passes through the capillaries at an average speed of, so this is by the heart, right? This is pumped by the heart, and this goes out, and this divides into capillaries somewhere, right? And in the capillaries, the average speed that the blood flows in a capillary, I'll take the capillary here, the average speed that the blood flows in a capillary is 1, it should be millimeter cube, isn't it? Okay, 1 millimeter per second. 1 millimeter per second, right? Okay, 1 millimeter per second of a speed is there. That is the velocity of it. A schematic of one capillary is given below. The cross-sectional area is given and the length is also given, right? Now the cross-sectional area is the diameter is given and the length is given. Okay. Assume that the blood is incompressible fluid having the laminar flow. So the number of capillaries the body is. Now it's basically you have to put A1 V1 equals A2 V2. Why? Because if it is a flow, there is either Bernoulli or continuity equation. Remember that. If it is a dynamic fluid, a flowing fluid, it's either Bernoulli's or the continuity equation, which is A1 V1. So basically, we can't put Bernoulli's to this, and it's basically A1 V1 because they are tubes, right? And this 6 liters per minute itself says AV. Why? As we discussed previously, AV is rate of volume, right? AV is basically rate of volume, isn't it? We discussed it, right? AV is basically the rate of volume. How? Because this is cross-sectional area, right? And this is length. A into L is volume and L divided by time is velocity. So A into V means A into L divided by T. So A into L is volume and it's volume divided by time, right? It's volume divided by time. So this is volume. It is volume divided by time. So AV, right? AV basically is volume divided by time, right? A is cross-sectional area, V here is velocity, right? Cross-sectional area into velocity equals volume divided by time. So this what I have given here is again 6 liters per minute, that is rate of volume, right? Volume divided by time. This is volume divided by time. So that is AV. So A1 V1 should equal to A2 V2, right? So A1 V1 is this 6 liters per minute, right? So do we have to convert this? So 6 liters is 6,000 cubic centimeters, right? Because 1 liter is 1000 cubic centimeters. So it's 6,000 cubic centimeters, right? Per minute. Shall we take it as minute? Yeah, of course, because it was given per minute, right? Yeah. So we'll take it as 1 minute. Anyways, this is A1 V1, 6,000 cubic centimeter divided by minute equals A2 will take one capillary first and this multiplied by number of available capillaries should be equal to this one, because the fluid should flow through each and every available capillaries. So that total volume per time should equal to the total volume pumped by the heart. So this is the total volume pumped by the heart. This should be total volume inside the capillaries, right? So we take one capillary into number of capillaries, like the rate of volume inside one capillary into number of capillaries should be equal to total volume pressed by the heart in a unit time, right? In a minute. So I'm going to take the A1 V1 or AB of the capillary, which should be 5r square. So 5, yeah, you can take it as 3. So 3 radius is 3 micrometers, which is 3 into 10 to the power minus 6, right? That is in meters. And if you convert this meters into centimeters, again you have to multiply it by 100. So that will be 10 to the power minus 4, right? This is now centimeters. So we are doing everything in centimeters now. I converted everything into centimeters, right? So like the 2r, the diameter is 6, so the radius should be 3, and micrometers is 10 to the power minus 3, right? 6 micrometers means 6 into 10 to the power minus 3 meters. So we need to convert it into centimeters. So I have to multiply it by 100. 3 into 10 to the power minus 6 multiplied by 100 is 10 to the power minus 3 into 10 to the power minus 4, right? So this is 5r square. Sorry, this is 5r. We need 5r square. This is 5r square, right? This is 5r square. This is the cross-sectional area, and this into the velocity is 1 millimeter per second. We have to convert it into centimeters again. If I divide it by 100, millimeter converted into centimeters, of course you have to divide it by 100. So that will be 1 over 100 centimeter per second, right? Centimeter per second. Either we could have like converted everything into meters, but because I converted this into centimeters, I did everything in centimeters now. So if you are doing it, converting it into meters would be good or preferable, right? So this is the volume rate of one capillary and this times number of capillaries N should equal to the rate of volume of the heart, right? Basically, so we have to simplify this one now. So it's a bit of a simplification there, right? So what shall we do? Okay, if I simplify this is anyway, is there any minute here now? I have to convert this into seconds because this is in seconds. I can't keep this in seconds. I'll convert this into minutes. Huh? So I'm gonna put seconds here because this is seconds here. So I have to keep this in seconds as well. 60 seconds. All good now. So 0 to 0 cancels out. 6 to 6 cancels out. There's 100 left here. Equals, if I take this one, 3 into, this is 3 into 10 to the power minus 4 square. That is 9 into 10 to the power minus 8 into 1 over 100. Right, 1 over 100. Now that will be another 10 to the power minus 2 adding to 10 to the power minus 8. This times n is there, right? So 3 into 9 is 18, right? 3 into 9 is 18. So I'm going to take it to this side. So 100 equals 3 into 9 is not 18, it's 27, right? 9, 18, 27. 27 into, now 10 to the power minus 8, and this is 10 to the power minus 2, adding them together 10 to the power minus 10 into n. I had to divide. How do I divide this? Now this will be n equals, did I simplify this correctly? I hope. Pi r square, right? Square. 3, 9, okay. Okay, so anyways, if I take it to this side, n will be what? N equals 100 divided by 27 into 10 to the power minus 10. That will be 1 over 27. 1 divided by 27. That is 0. Sorry. This is what I have received so far. 0.03703 sort of continues. Multiplied by 10 to the power 12. I have 10 to the power 12 here because of the 100. Because the 100 is 10 to the power 2, and this 10 to the power 10 is adding together, is becoming 10 to the power 12. Is there any sort of answer? Yeah, right. This one. So if I 1, 2 decimals, that will be 10 to the power. It has given as 9, close. It's so close. The answer should be this one, right? Answer is this one. So did you understand that one? I hope you understood it, right? So A1 V1 equals A2 V2, right? We had to basically apply there. A1 V1 in the heart is equal to total A1 V1 in the capillaries. That's all. A1 V1 in the heart is equal to total A1 V1 in the capillaries. That's what it's about, right? So let's go to the next one. 8th question. The mass of man wearing a pair of shoes is 52.8 kilograms. The total sole area. So those questions we discussed were a bit difficult, right? So bit of a difficult one. So if you can manage it, then it's okay. And it's still under the physics questions, and they are the very last questions of the paper. And this is past paper classification we are discussing. This is not hard questions in a row. Okay, this is not like hard questions in a row. This is separate questions in each past papers, and each questions from each years can be difficult, and that's okay, right? So come to this one, 8. So this seems to be becoming easy now. So the beginning the fluid mechanics was really hard. Now it seems to be becoming easy. Let's see. So the calculations were a bit difficult at the beginning. Now it seems to be becoming easy. Right? Let's see. The mass of a man wearing a pair of shoes is 52.8 kilograms. The total sole area of the pair of shoes is 176 square meters. What is the pressure exerted by the man on the floor? That's easy, right? So it's pressure equals force over area, right? So force is what? The weight of the man. That is 528 newtons, right? That is 528 newtons. And area is what? Area is 176 square centimeters, but we have to take it in square meters. So converting square centimeters into square meters is, you have to divide by 100 to convert centimeters into meters. You have to do it twice to convert it to square meters. That is 10 to the power minus 2 into 10 to the power minus 2. That is 10 to the power minus 4. So what is the area? The area 176. So 176 into 10 to the power minus 4. This is the total area. So let's divide this. 528 divided by 176. That is 3. So 10 to the power minus 4 going up becomes 10 to the power 4. 3 into 10 to the power 4 is 30,000. So it's 30K, 30,000 Pascal. That's easy. That was easier. So now it seems to become it's becoming easy. A piece of wood with the relative density of 0.27 floats on oil. Relative density, again. A piece of wood with relative density of 0.27 floats on on oil of relative density 0.81. So the relative density of oil is 81. So you just have to multiply these two by 1000. So you get the actual density. What is the volume of the piece of the wood that appears above the level of oil as a percentage of its total volume? Ooh, that's a bit of a tough one. Not very tough. Let's see. Right. So two of the things are given. What are the two of the things given? You are given with, two of the relative densities of oil and a wood, right? So there's a wood here. Take this as the wood. This is the wood. Right. So this is the wood. And the relative density of the liquid is 0.81, right? This is 0.81. And the relative density of the wood is 0.27, right? This is 0.27. That's what the question says. Right? Yeah, right? Yeah, 27, right? So level, they're asking for the volume of the piece of wood that appears above the level of the oil. They're asking for this volume, this part, this one. This volume as a percentage of the total volume, right? Percentage of the total volume. Okay. So the upthrust should equal to the weight, right? U should equal to mg. The upthrust is given by the part that is immersed. So if we take it as because it's floating, now mg should equal to u, the upthrust, the weight and the upthrust should equal, and mg should equal to v rho g, right? V rho g. Okay. So now, the weight of the, I'll take the total volume of this as V. Okay. The total volume of the cube is V. And we know the density, relative density is given. So the density should be this multiplied by 1000. That is 2073 kilogram, sorry, 270 kg m cube, right? If this, it should be 810 kg m cube, right? So now we know the density D equals mass over volume. Density equals mass over volume. So density multiplied by the volume gives you the mass. Get it? So here, instead of mass, I can put, I can put mass equals density into volume. So I'm going to apply density into volume. What is the density of the cube is 270. So 270 into volume, I took it as V. That is mass into G. This is mg now. Equals, now this V is the part that is immersed, right? Part that is immersed. If I take the volume of this part as V naught, right? I'll take this as V naught, right? This volume should be, right? The immersed volume should be V minus V naught, because we don't need the immersed volume. We want this part, right? So because of that, I'll take it as V minus V naught is the immersed volume, which gives the upthrust, right? So V minus V naught times, is the density given? Yeah, the density is of the liquid is 810, right? And the gravitational acceleration is g. Anyways, g to g cancels out. Now you just only have to find V over V ratio. Yes. Let's simplify this. So 270V, right? 270V equals 810V minus 810V minus 810V naught. So take the 810V naught to this side, take 270V to the other side. That will make 1080. Sorry, 810V naught equals 810V minus 270V. 270V. So how much is 810 minus 270? That is 810V naught equals 540V now. So what we need actually is, it's not V naught, this is V. What we need actually is the percentage of volume that is on top to the total volume. That is basically V naught over V. So isolate V naught over V. Take this V to this side. That will be V naught over V. Take the 810 to the other side. That will be 540 divided by 810. Now this into 100% is the percentage of it. This into 100% is the percentage of it. Right? So we need V naught over V. V naught over V percentage. So this is it. 54 divided by, 54 divided by 81. Right? 54 divided by 81. That will be 0.66. So 66.66%. Yes, 66.66%. Right. Is there an answer? Yeah, so 66.6 is 67 round off, right? 67 round off. Understood it? So the fluid questions are somewhat good. Hope you understood it. Huh? Is this good? Yeah. Right. So come to this one. Functions of the Bunsen burner can be described by using the Bernoulli's principle. If the pressure at point A, B, C of the Bunsen's burner shown in the diagram are PA, PB and PC respectively, what is the correct relationship between them? They're asking for the correct relationship between them. So now, so let's think about it, right? So here, look at this one. Now, atmospheric air. No, it's actually the LP gas coming. So it's coming under the pressure on the atmospheric air. Sorry. The atmospheric pressure is actually there. Here, the atmospheric pressure is there. So gas is coming under a pressure. So because of the narrow tube, now the pressure, the velocity increases, right? Because of the narrowness. Remember, when the velocity increases, pressure drops, right? So because of the narrowness, the velocity increases, pressure drops a little bit. Let's say pressure drops a little bit and comes to here. And again, do you see that there's a nozzle here and it's narrowing? So again, the velocity is increasing here and the pressure is dropping. So there's a lower pressure here, right, compared to the atmosphere. Now, because of that lower pressure, the atmospheric air is sucked in because the pressure here is low, the atmospheric pressure is high. So because of the pressure difference, the atmospheric air is sucked in with the LP gas, and these two, atmospheric pressure and the LP gas, both goes to C and burns as a flame. So that's what happens. So if we compare A, B and C, you know, because the narrowness of the tube here, the pressure B is low, right, is low than pressure A, and it seems there is no change here in the tube. Point B and C is the same cross-sectional area, so PB and PC seems to be equal. If there's something like that, we have to compare. No, right? Anyways, PA is greater than PB. PA greater than PB. Nothing like that. This one. PA is greater than PB. Right? Pressure A is greater than pressure B. Otherwise, the air won't come out because there has to be a pressure difference to air to flow. So the pressure here must be greater, pressure here must be less, because otherwise the air won't flow. Obviously, the A is greater than B. There is only one answer. A is greater than B, that is 5. So we don't have to worry about now PC, because we know that PA and PB relationship should be P is greater than PB. Now PC, because this is uniform, I just thought it should be the same pressure because it's not narrowing or happening anything. But it says the pressure has increased, right? No. The lowest pressure is there at PC. Maybe can happen because this is burning. This is burning. The air is removed from here, so the pressure is dropped because the air is removed from here because of the burning. The air pressure is dropped here. Therefore, C can be very low pressure there. So that's true. That's true, anyways. So, anyways, the answer is 5. Hope you understood the logic. So, okay. 11th question. What is there? Okay. So, when water is at rest, heights of the water columns H1, H2 and H are the same as given in the setup. What is the correct relationship among the heights of the water column when water flows steadily and non-turbulently, streamline flow? To the right, at the constant rate. So if the water flows through here, we'll have to think about the pressure and the velocity. So when the narrowing happens, the velocity is increasing. So if the velocity is increasing, pressure is dropping. So towards this way, pressure is dropping. If I take this one, P1 is greater, P2 is less, P3 is the lowest pressure. So if the pressure here is high, which means it will press the air column up, so the height of this one will be greater. And this here, the pressure is less, therefore the pressure won't be pressing the water column up, therefore the height here should be less than this one. And pressure here is the lowest, therefore the liquid column isn't pressed up, so it goes really down. So it's H3, right? So H1 is the greater, H2 is next, the last is H3. Okay. So they have mistakenly put H1, H2. Now it should be, maybe if it is H3, this is the answer. So anyways, the answer is this. Sometimes the typos are there. Right? Typos are there. Okay. I come to the, this is, yeah, that's finish, right? That's finish. So far it. Right. We will discuss some more on electricity and the fluid mechanics as well, right? So those few questions are really good. I hope you understood it, right? Go through it again, you'll understand more. So let's wind off for today, shall we?